Good morning. My name is Mark Wilkinson. As was said, I'm from the University of Leicester. I'm director of the DiRAC HPC facility in the UK. So I'm an astronomer by background, but today I'll be presenting a mixture of results from astronomy, cosmology, and particle physics. And I'll also be showing how what we do by working with our partners in the HPC industry, we're able to deliver much more science from the systems that we have in place. So the Science and Technology Facilities Council are the funders of the DiRAC facility. We get our capital funding direct from the government through Department for Business, Energy and Industrial Strategy, but it's STFC provide the operations budget and it's essentially their science that we're delivering. So DiRAC provides HPC resources. It's a national facility, and it provides HPC resources for the theoretical physics, theoretical astrophysics, particle physics, cosmology, and nuclear physics communities in the UK. So essentially all those communities, any of them that are using HPC will be using DiRAC resources. We've got 4 systems scattered around the country. The extreme scaling system in Edinburgh. Data intensive is split between Cambridge and Leicester. So for those of you who are attending in September, that's where you're trying to get to. And the memory intensive in Durham. In total, we've got about 90,000 cores, 5 petaflops of theoretical peak, and more than 10 petabytes of storage. Now, I'll talk in more detail about each of the systems and explain why it is we have these multiple systems in the rest of the talk. So just to give a quick history of the facility, we came together in 2009 as DiRAC-1, and at that time we were essentially just, it wasn't really a facility, it was just all the groups in the UK that were using HPC to do their research joined together to form one large collaboration. So we had parts of systems at 13 different sites. In 2011, we consolidated that down to 5 systems in 4 sites, so Cambridge, Durham, Edinburgh, and Leicester. The thing we were very proud of in that we did the procurement of all 5 systems in 100 days. So it was 100 days from the day that we got the money to the day that the money was actually out the door and spent and the systems were installed. I wouldn't recommend it. We're all going to die younger because of those 100 days. So in December 2012, we turned the systems on. The great thing was because we had co-designed the systems with both the researchers and industry, it meant they were exactly what people needed to get started instantly. So within about a week, all the systems were full, and they've been full ever since. And so that's something that we try very hard to do at each time we redeploy upgrades, is to make sure that we're using them from day one. And so that requires a lot of advanced work in terms of preparing the community to be able to use whatever hardware we're putting in place. But it means that the science impact of the facilities is as good as it can be. All access to it is controlled by an independent peer review panel. So as director, I have a little bit of discretionary time, but most of the systems are allocated by independent peer review. And it's free for STFC-funded researchers, and we do have some time available for industry if anybody's interested. Excuse me. In April 2017, we were hoping to have already deployed DiRAC-3, but the government was still discussing how they would fund it. So we got a small amount of additional funding for DiRAC 2.5. We then consolidated into what we call 3 services: extreme scaling, memory intensive, and data intensive, and this was around different types of workflow. In 2018, because DiRAC-3 still hadn't arrived, we deployed what we called DiRAC 2.5X, and this was funding to replace the hardware that we'd had in 2012. At the end of 2018, because DiRAC-3 still hadn't been funded, we deployed DiRAC 2.5Y, which was a factor 2 upgrade of all the services. We are hoping DiRAC-3 will be the next thing on this slide, because if it isn't, we should have started with 2.5A instead of 2.5X. So why do we need HPC? So I probably don't need to belabor this point to this audience, but the one thing I would stress is that because direct simulation and modeling is key to the theory community, HPC systems are the scientific instruments for the theory community. And the reason I put it that way is that's a very important principle, because that decides who should be designing them. If we were talking about a telescope or a detector, it wouldn't be government that was designing it. It would be astronomers would be designing a telescope, or physicists, or whoever would be designing the detector. So it's very important that the research communities are involved in the design or the co-design of the systems, because they will be using them to do their science. The computation requirements obviously are increasing for a number of reasons, because we're trying to do either higher resolution models with the same physics to try and get a better understanding of the physics we already know, or we're putting new physics in, so the models are becoming more and more complex. Also, a growing area is that we're trying to do multi-scale modeling, so you're looking at, as you increase the resolution, you often have to increase the physics that you put in. And then finally, we're now trying to understand the uncertainty in the model. So you don't just want to run one big 5-month simulation, you want to run 10 so that you can get a sense of how the outcome depends on what you put in. And so we're under, just like in any field of science, we're constantly trying to refine and redefine the tools that we use. So just like the telescopes over time improve and are refined and used in different ways, it's the same with HPC for the theory community. There's also a growing requirement that the simulations and the models be done concurrently with the taking of data. So the next generation of large-scale surveys are often going to be taking data, modeling it live, so that they can then decide. They won't be able to store all the data that they're taking, so they have to use models to decide which data are the most valuable. So that's going to increase the amount of computing resources required to do the modeling live, and then post-processing and the actual scientific output of those facilities will be done on even larger systems. So our approach to designing services is we always start from the science case. So the first thing we do is we get the research community to write down all the questions they want to answer over a period of, say, 3 to 5 years. We get that externally peer reviewed, so that then we have a basis of what it is we want to do. We don't ask the researchers at that point how they think it should be done. Whether they think they know the answer to that or not, it doesn't matter at that point. It's just what do you want to do, and how big are the kind of calculations you're expecting to need to do. We then go through a process of assessing the workflows associated with that science, and that leads us to high-level technical specifications. And we get that set of technical specifications peer-reviewed as well, so that's by people who are expert both in HPC and the science, so that they can assess whether it is an appropriate solution that we're suggesting. Then we go through an extensive co-design process with our industry partners to see how we actually deliver that in practice. And that leads us down to the individual service specifications and what we actually put on the ground. And that's what led us to the 3 services that we currently have. So we have the extreme scaling system in Edinburgh, which it's a 2 petaflop system. It's for particle physics, so lattice QCD simulations, and it's the hypercube interconnect is one of the key features of that system, because it's perfectly balanced for doing lattice QCD calculations. Over on the right, we've got the memory-intensive system. That's for doing large-scale cosmological simulations that scale well, provided there's enough RAM to help to give each node enough data to work on. And so we've also got a novel flash volume associated with this system to allow faster checkpointing that I'll talk about later. And in the middle, we've got the data-intensive service, and that's a range of architectures. We've got GPUs, Skylake, and Xeon Phi, and now more recently some ARM. And this is a range of architectures, and that's for a very diverse set of science workflows, but all focused around being data-intensive. So before I go into discussing the details of each services and showing you some of the kind of science that we're able to do with them, I'll just show off that this process does actually work. So this is one of our kind of PR slides on publications. So the the good thing we've been able to do is, because we're a research facility, one of our KPIs, so the key things that we're judged on is how many papers we produce, which is good because that's really the whole purpose of the facility. So what you've got here are papers published in each year. So 2014, if you look at this one, and the colored bars are the citations from 2015, 2016, 2017, and 2018 for those papers. So we're publishing at a rate of about 200 papers a year from the community across the UK. The key thing is that this shows the citation counts are high and staying high. So we're actually publishing a significant number of papers in high-impact journals, and they're also being cited consistently over time. So we're not just kind of publishing papers that people read and forget about. So, okay, that's enough boasting. I'll now go and move on and talk about the services and the science. So the extreme scaling service in Edinburgh, it's based around an HPCAC-AI 8600. It's just over 1.8 petaflops in total. It's based on Skylake 4116 processors, so that's silver processors. The reason for that was a decision that there was a lot of discussion about whether that was the most appropriate, and that for the problem that we were looking at, that produce the most balanced system in terms of compute and memory bandwidth. There's 96 gigs of RAM per node, and also now in the latest deployment there's also 8 GPU accelerated nodes, and so this is to explore the next generation. It's getting us ready for the design of future systems, which are going more likely to be a mixture of Skylake and accelerators. And so those GPU nodes each have 4 Volta GPUs in them. It's got a Hypercube OPA interconnect and 3 petabytes of storage. So to give you some background as to what it is we're trying to do with this, I'll try and teach you all of particle physics in about 3 slides. And I'm not a particle physicist, so this summarizes my knowledge as well. So what you have here are the 5 forces of nature. So in everyday life, as it were, now we see electric, magnetic, weak, strong, and gravity. So we're all familiar with gravity, electric, and magnetic, and weak and strong are the forces that hold particles together in atoms and in nuclei. And as you go to higher and higher energies, these forces join together. So electric and magnetic join together. At higher energy, electromagnetic and weak join together to give you electroweak, and strong. Quantum chromodynamics looks at the strong force, and they join together at higher energies with the electroweak. You've got one force, and we think at the highest energies, gravity will join together with all these forces, but the joining there is dotted because we don't yet have a theory of that. So what we'd like to do is we try to use the matter that we see around us to understand the properties of all of these forces. And so on the theory side, we're trying to calculate the detailed properties of particles so that we can pair with observations that can teach us about what forces are at work. So if you look inside a particle like a proton, there are 3 smaller particles called quarks. So in the case of a proton, you've got 2 up quarks and a down quark, and they're held together by the strong force. Now, you don't get quarks on their own, so what you have to do is you have to smash them together. You have to smash protons together or other particles together, and by looking at the products of what comes out, you can try to understand what the structure inside them was, and that helps you to learn about the nature of the strong force. And so when you have a collider like the Large Hadron Collider, where you're smashing particles together, that actually, by looking at the particles that are produced in the collisions and by looking at the rates at which those particles decay after the collisions, that tells you a lot about what the details of the forces inside the particles are. And so what we're trying to do on the theory side is calculate all of these quantities from a theoretical perspective, so essentially starting from just the Schrödinger equation or the DiRAC equation of quantum mechanics, and actually calculate from first principles what these decay rates would be, and then compare them with what's measured. So in practice, what that means is you put down a lattice in space-time, so it's a 4D lattice. So that's 3 space dimensions and the time dimension. And what you have is, if you look at this example here, you see that each of the dotted area, each dotted cell, that's the unit cell. So that's the bit where you actually have to do a calculation for your finite difference calculation of the partial differential equation you're trying to solve. So at each point, you have to talk to the points just directly beside it. Wherever there's arrows, that's where you're going to have to talk to something which is outside the stencil that you're looking at. And these gray bits are places where it's periodic. So essentially, this part wraps around to here, this part wraps around to here, so it becomes a tube, and then the 2 ends wrap around together, so you end up with a kind of donut shape, the torus. And when you work out the details of it, you find that 1/L of the data references in a calculation like this come from off the node. So that's what's going to decide how the internode communication, how good that is. That'll decide how efficient you're at and how much you're able to scale these kind of quantum chromodynamic calculations. So in order to make it scale, you need a network bandwidth, which is given by this relation. So it's memory bandwidth divided by L, where L is the size of your grid, times R, which is a reuse factor. So that's how, whether you're able to reuse the stencils, or how often you want to reuse the stencils in the cache. The aim is to distribute 100 to the 4, so that's 10 to the 8 data points over 10 to the 4 nodes. So as I said, the key thing is, the limiting factor is moving the data around. So when you need to talk to something that isn't on the node that you're working on. This slide summarizes the problem. So hopefully you can kind of see it. So this is petaflops, single point. So this is node teraflops, and this is communication in gigabytes per second per node. And so as you're, I'm sure, well aware, this is basically showing various different systems either in existence or in the near future. So there's a significant increase in the overall performance of the system in terms of peak petaflops. The nodes are getting significantly more powerful, so you've got more than a 400 factor increase in the single point precision node performance, but the bandwidth is not increasing. So and what that means is the systems aren't as balanced as they were. And so for a QCD calculation, that's not a good situation. So the way that this has been resolved within DiRAC is twofold. One is to work on the code, and one is to work on the hardware. So in terms of the code, it's a code called Grid Quantum Chromodynamics. And the considerations that were taken into account in terms of designing the code are summarized here. So they wanted it to be portable across multi and many core CPUs, and so that meant using a mixture of MPI, OpenMP in the node, and then SIMD. Likewise, it should also work on GPUs, so you could take advantage of accelerators, and so that's MPI with offload and SIMT. As I said, the arrays that you're looking at are n-dimensional Cartesian arrays. Multiple grids are being used, so essentially what it does is it subdivides every grid and uses copies of the grid multiple times in order to be completely SIMD parallel. And that was based on inspiration from the connection machine in the 1980s. And the other thing then, so that was on the software side. On the hardware side, it was looking at the interconnect. And so the idea here was to make sure that the interconnect was exactly matched in to the calculation. The details are given there. So essentially, the summary was the 8600, the HP 8600 was customized so that it has 2 to the 4 nodes per leaf switch. And when you do that, what you see here, this is the the performance per node as a function of the number of nodes in the calculation, and the different colors are different sized, different volumes of calculation. And what you see is that it's very well balanced, so it's scaling extremely well. So as you go to a larger problem where you use more nodes, you're still getting essentially the same peak performance out of the nodes. It also is using 76% of wire speed in every link. And so again, that's an extremely good use of the system, but it's, and this required both the design of the hypercube interconnect plus the fact that it was using the smaller core count nodes. So just as an aside, another thing that's been designed by the team in Edinburgh in collaboration with Intel and the Alan Turing Institute is work on, so not just on particle physics, but also on machine learning. And so this is a new numerical format, so it's called BFP16. So essentially it has an 8-bit exponent and a 7-bit significant. And what this is, so this format, and there's a patent has been submitted, the number is there. The idea here is that by using this format, you're able to get faster convergence of machine learning when it's being trained. So what you see here, this is the number of iterations for, this is AlexNet and ResNet, but you're seeing that's with the IEEE standard FP16, and this is with the new format. And in both cases, you see that it takes fewer iterations, you start to converge faster. And essentially this is because the idea for this came from looking in detail at the what was being calculated, the results that were being calculated during the gradients that you have to evaluate during the process of training the algorithm. And one, again, on the AI side, work that Peter Boyle at Edinburgh has been leading on. Sorry, I should have noted there that, so Peter Boyle is the technical director of DiRAC, and Sid and Angus now work for Intel, but they used to work for DiRAC, so they were two of our first research software engineers who, as soon as we ran out of funding to continue their contracts, Intel, who were working next door, very kindly poached them. So, with apologies to Intel who are here. Other work that Peter Boyle has been doing was to, and again this was with Sid and Angus, was looking at the Baidu research algorithms, and they took the, this is the time to solution and against the number of words. And essentially the idea here was they took an algorithm which was already optimized for cloud, and they took it apart and then redesigned it to look at how you would implement it if you were trying to implement it on an HPC cluster. And what they found was that by re-engineering it, they could get a factor 10 performance improvement. And so it's interesting because it shows that there's often this implication that everything should be done in the cloud, but actually this is saying that there are times when even, and certainly that everything AI can be done in the cloud. This is showing that actually with enough work on the design of the system and tailoring the code to take full advantage of the system, you can actually do machine learning more effectively on an HPC system in this particular case anyway. So it's not that it's always going to be like that, but it certainly shows that this artificial divide is a bit spurious. So finally, some science that has come out of the new system at Edinburgh using all the hardware and software that I just described. So what this is another case where you're trying to identify new physics by looking at the properties of particles. So the type of particle, mesons, unlike the proton that I showed you earlier, which had 3 quarks in it, mesons just have 2, so they're made of a quark-anti-quark pair. And the rate at which they decay, which is called F, So that's what's plotted on the y-axis of these plots. So the decay rates are a very strong test of the standard model of particle physics. So when you see a discrepancy between an observed decay rate and a calculated decay rate, it's often, telling you something about, so it may be indicating that there's some aspect of the physics that hasn't been taken account of. And so one of the groups using the DiRAC systems has developed a computationally very efficient way of calculating these decay rates. So they start out with a calculation at this point here, where they calculate it assuming that all the quarks, so the different types of quark, all have the same mass. Then they repeat the calculation for different quark masses, so the different dots you see are where they've calculated for different quark masses, and then they extrapolate down to physical quark masses. So over here, the dotted line, or the solid line there, are the actual physical quark masses. And the stars in each plot are the measured values. Here you then extrapolate down. So in the case of in the case of this, which is the kaon and the pion mesons, a linear extrapolation does reasonably well in terms of going from where you've calculated to the measured value. In the case of these are B mesons, you see that where you do a quadratic fit rather than a linear fit, the quadratic fit gets closer to the true value. So again, that may be pointing to changes that are needed to our understanding of the underlying physics. So now moving on to the memory-intensive system. So this is the system at Durham. It's called COSMA. It's got two components that are still running. One was an IBM Lenovo DDN system from 2016, and it's based around Sandy Bridge. It's got it has 8,000 cores, 2-to-1 blocking, and 65 terabytes of RAM combined across the system. And last year, Dell installed a new system called COSMA 7 with 23,600 Skylake cores. It's also 2-to-1 blocking. It now has 230 terabytes of RAM. The reason for showing the combined RAM is that essentially sets the scale of the biggest simulation that you can run. The key thing is that it's got this fast checkpointing system, so a flash-based checkpointing system. And I'll show the advantages of that in a moment. So what we're trying to do with this is we're trying to simulate the whole history of the universe. You start from the Big Bang. You look at the early universe with some small fluctuations. There's a period of inflation where those small fluctuations, which are quantum, become large enough, are expanded to a scale where they become essentially the initial perturbations that drive the formation of all structure in the universe. So this is the microwave background, which is a kind of an imprint of that. And then 14 billion years later, you've got stars and galaxies and planets and us. So the ingredients that you need are atoms, so that's all the normal matter that we're familiar with. That gives you the stars and the gas. That makes up about 5%. About 26% is dark matter, which we don't know what it is, but we know that it's there and it's heavy. And dark energy, which makes up the majority of the mass energy in the universe. We don't know what that is, but we think it's there, and it makes the universe expand more quickly now than it did in the past. So in DiRAC, we're looking at all of these in different ways, but for now, I'm going to focus on the atoms and dark matter. Just to give you a sense of how quickly things change in cosmology. So when I started my thesis in 1996, dark energy was not part of this. So it used to be that this was 5% atoms, 95% dark matter. So when I started my thesis and I was working on dark matter, I was looking at 95% of the universe. By the time my thesis ended in early 2000, dark energy had appeared. So I had been relegated to about 25%. Instead. But it just shows how it's a very rapidly advancing field. Now that there's a lot of data coming in from satellites, it's no longer just a theoretical field. So this movie shows the formation of structure in the universe. The first movie I'm going to show, actually, could we dim the lights? Because that would make it easier to see. Yep, I'll go back and start again. Thank you. So what you're looking at here is the dark matter in the universe. And so early on, it's relatively uniformly distributed. There's just small fluctuations in density, so some bits that are a little bit higher density. Over time, then, gravity makes the dense parts get denser, and more matter flows into them. And so what you're looking at here is where it's bright, so the brightness gives you a measure of the density, and the color gives you a measure of the typical velocity of the dark matter particles. So where it's yellow and bright is a place where the dark matter particles are moving quite quickly, so that means maybe 100 kilometers per second, and it also means, because it's bright, it means it's very dense. So what these simulations, which were led by the Virgo consortium it's an international consortium, but it was the team in Durham that carried out these simulations on the DiRAC memory intensive system. So these are the Eagle simulations, and they're trying to form a galaxy like the Milky Way. So what you have here is up in this bright part, that's where the Milky Way would be. And as you can see, it's surrounded by a halo of smaller galaxies. Some of those we see, some we don't. So it shows that there's a lot of substructure around, and now we're just zooming out to show all the other galaxies around it. So that was dark matter only. So that's essentially all the stuff that we can't see. So if we look at the simulation again, this is exactly the same simulation, but this time you're looking at the stars and gas. So again, it starts out fairly uniform, and now you'll see that you've got gas flowing into the same region. And again, the whole simulation is spinning around. The color gives a measure of the temperature, and the brightness gives a measure of the density. And what you'll see is every so often there's a burst where you suddenly get a wave of gas moving out, and that's where some of the gas has fallen onto the black hole at the center of the galaxy, released a load of energy, and that energy has then sent out a blast wave which reshapes all the gas around it. And so now here you can see that you've got this swirling pattern, and that's what gives rise to an object like the Milky Way, because the Milky Way is a disk galaxy, so it is actually rotating. That wasn't obvious in the previous simulation where you looked, where you could only see the dark matter. And what the other interesting thing is, this simulation goes right the way to essentially the present day, and what you notice is there's still lots of stuff falling in, both dark matter and gas. And so that is what we believe is happening. The Milky Way is still accreting other galaxies, smaller ones, onto itself. And again, if you look in the vicinity, you've got other large galaxies nearby. So one of these ones would be the Andromeda galaxy. And if you ran the simulation forward another 5 billion years, you would find that that galaxy collided with the Milky Way and formed a new combined galaxy. So that's the kind of simulation that we want to be able to do, but we want to be able to do more of them and at higher resolution and add in more physics. All the physics that in there is just an approximation to the real, to really what's going on. We want to be able to do it at higher resolution. So that's where we need to both design the system appropriately in terms of hardware and use research software engineers. So that's a quote from David Keyes, that when we're buying these extremely expensive systems using public money, we should be making sure that we're using every last flop that we can on them. And so we know from the science case for the next generation system, we need a 10 to 40 factor increase in computing power to stay competitive. And the UK government will not give us enough money for that. So we have to allow for the fact we're going to get some increase in terms of the power of the system, but we're going to also have to work harder in terms of the software. And as you know, it's getting harder to extract. To get more flops out of the newer hardware is difficult, and it's a place where increasingly the astronomers and particle physicists don't necessarily have the coding skills to be able to do that. So there's a large community now in the UK of research software engineers who are essentially the interface. So they have both the science background to be able to work with the researchers and the coding skills to be able to write the code more efficiently. Because some people can do both, but they're few and far between. And so we want to make sure that all communities are able to access the best HPC and exploit it well using the right software. So at the moment we've got 3 software engineers. We're hoping to have an increase of 2 or 3 in the next year. So in the context of the simulations on the memory intensive, the cosmological simulations, so we invested quite heavily, both in collaboration with an IPCC funded by Intel and one of the DiRAC software engineers, and we've developed, the team at Durham developed the Swift code, which is about 20 times faster than the code that I showed you that did the Eagle simulations. And so the idea of that is it uses task-based parallelism to be much more efficient in terms of how the workload is distributed across the nodes. And that means that they're currently starting to do the next generation of simulations, which will be able to include more physics, but still be able to complete the runs on timescales that are reasonable, which is kind of 5 or 6 months. The other big thing that we added to the memory intensive service is a burst buffer for checkpointing. So this was a flash-based volume. It's about 340 terabytes. And the key thing here is this greatly reduced the amount of time taken for doing checkpoints and for doing snapshots. So if you're running a simulation and I'll just note that it's working extremely well. So we've actually got to the point where the theoretical peak was 185 gigabytes per second, and on user codes we're getting up to 180. So it really is performing extremely well. But the crucial thing with it, the value of it is shown in this plot and on the next slide. So what you'd like to do is while you're running the simulation, maybe for 5 months, you'd like to be doing a snapshot, ideally, maybe once a day, probably more often, maybe every 12 hours or every 6 hours. And what this plot shows is, depending on what the bandwidth is, so 30, 120, or 140 gigabytes a second, this shows the power you would use over 5 years if you were running consistently for 5 years and every 24 hours you were doing a snapshot. And so you can see there's a huge power saving when you go to using a system like the checkpointing that we're doing now with the flash-based checkpointing. So in terms of power, it's extremely efficient, but in terms of the science, it's extremely useful as well. So what you've got here is, again, depending on how often you want to do the snapshots, this is how many core hours you lose. Right, thank you. This is how many core hours you will lose doing checkpoints. And so if you look here at 30 gigabytes a second, if you're doing checkpoints every day, you lose 7 million core hours over 5 years. Given that you've only got 36 million core hours a year, that's quite a big chunk of time. And so what they found is that in a typical 5-month simulation where you're doing snapshots every 12 hours, you've essentially got 13% more core hours available to do the simulation. So effectively, by putting in this additional burst buffer, it costs, it's not free obviously, but given that it basically makes the entire system about 10% or 13% more powerful, it's a really good investment, or we have found it a really good investment. And a cool simulation that they've just done with the memory intensive service and the Swift code that I mentioned was, you may have seen this on the news, it was around beginning of the year, where it was simulations of the planet Uranus, and because it has an unusual spin axis because it doesn't align with the plane of its orbit. And what you're looking at here is a simulation of a very large object colliding with Uranus, and essentially that collision leads to it having an axis which is spinning. I think it's almost up at 90 degrees to its orbit. And over here, you've got this is the atmosphere of Uranus. This is ice and this is rock. Similar over here, you've got rock at the center and ice around it. And over here, you've got the internal energy of it. And the point of showing these plots is essentially just to show it's the largest planet collision, the highest resolution planet collision simulation that's ever been done. And you can see there's a lot of structure in both the distribution of the particles and the distribution of energy. So there's obviously an awful lot you can learn about the details of how a collision like that affects the internal structure of a planet. I'll just briefly mention gravitational waves, because it's always good to mention gravitational waves in any science talk. So gravitational waves were discovered very recently, having been predicted by Einstein 100 years ago. And the DiRAC was involved, so the LIGO consortium were the team that actually did the discovery, but the DiRAC systems were used, so the LIGO team in the UK were using the DiRAC systems, the DiRAC system at Durham to do the simulations to interpret the data, because essentially what you see is, you see this characteristic chirp signal, but it depends on what it was that it's produced by the merger of something, probably black holes or neutron stars, but depending on the details of the masses and the orbits of those black holes, you'll get a different signal. So in order to actually interpret what you see in the raw data, you have to do huge suites of simulations so that you've considered lots of different mass ratios and different orbits for the objects. And so some of those simulations were done on the DiRAC system. Now I'm running out of time, and I did say I would try to use up time that was left over from yesterday, because apparently some of the talks underran yesterday, but I don't think I was believed. So what I'll do is, so I'll just show a couple of slides about the data-intensive services just before I finish. So at Leicester, we've got 400 nodes of Skylake. This is an HPE installation. And this is based around Skylake Gold. We also have a 6 terabyte Superdome Flex node and 3 FAT nodes with 1.5 terabytes. And again, this is driven by various workflows that need large-scale shared memory. We've 150 terabytes of flash storage, which we're currently getting up and running to be able to use as part of workflows in a different way to the checkpointing workflows at Durham. We've recently installed an ARM-based system. So this is HP, ARM, and SUSE Linux. It's called Catalyst UK, and they put 3 ARM-based systems, one at Leicester, one at Durham, and one at Leicester, one at Edinburgh, and one in Bristol. And it's got InfiniBand all-to-all interconnect, and we're using that to explore where ARM would fit into future HPC computing. At Cambridge, which is the other part of the data-intensive service, we have a mixture of architectures there as well. So we have a large Skylake system, so it's about the same size as the Leicester one, slightly larger. We've got 44 KNL nodes and 12 GPU nodes. Now, these don't seem like very large numbers. The key thing is this is a shared service between DiRAC, University of Cambridge, and another research council, EPSRC, so that's the engineering and physical sciences. And so actually this is 12 GPU nodes, but that's a 13% share of a larger system. So this is the bit that we actually own, but we have access to about 10 times that in terms of the overall performance. There's also 1.5 petabytes of storage, and this is an OmniPath-based system, and all of the different architectures can see the same storage. So the idea here is you can have a workflow which uses multiple architectures, but doesn't have to then, you don't have to transmit data because it's all in the same storage. And the other thing is this flash-based storage, the data accelerator, which again is going to enable data-intensive workflows, so everybody can write into that flash storage and then read it out again very quickly. And so the kind of simulations that we're doing on Okay, I'll move to this one instead. So this is an example of the type of simulation that we do that's being done on the data-intensive system. Here you're looking at clouds of gas turning into stars. So you're coming down in scale from whole galaxies just to much smaller regions to look at how exactly stars form. And the difference between the different simulations is they all start out with the same amount of gas spread out in the same volume, but they have different amounts of metals. So anything that isn't hydrogen or helium is called a metal in astronomy. And so what you see is up in the top left, you've got very low metal content, and down in the bottom right, you've got very high metal content. And the point of this is it's the first systematic study of the impact of having significant variations in the metal content of gas in terms of what happens at the end. So as I say, you start out with the same amount of gas, but you can see that down here, where you have very high metallicity, so a large metal content, every place there's a dot is where you've got a star forming. There's a lot more stars here than there are in the lower metal one. And so this shows, this study is looking at not only, the other thing you may have noticed is there were more explosions so there was only one big explosion here, so it affects the number of stars that you get, and the types of stars and the masses of the stars also vary depending on the metal content. The last thing I'll mention is training. So this is a key thing that we provide, as well as the science output. We're also training postdocs, PhD students, and academic colleagues. So at the moment, we don't provide the training ourselves. We're basically a portal for access to training that exists, whether that be in the universities or in industry. We have a test, it's called the DiRAC Essentials Test. It was the first, essentially, driving test for HPC in the UK, and that's just to make sure that everybody has a basic level of skills before they use our systems. We also have run multiple workshops. We're running hackathons with various different industry partners to get the community much more used to interacting with industry partners and to improve the quality of our codes. We're going to be organizing domain-specific workshops and also putting together a training portal for our students so that students can pick not just academic-focused but also industry-focused training routes. Now, why do we do that? Obviously, it helps to improve our science output. That's the key perspective from the facility point of view. It also means that we're able to take advantage of new hardware as it comes out. What we don't want to do is buy new hardware and not be able to deliver science from it effectively. And in terms of our contribution to the wider world, it also means that we're generating a lot of our PhD students obviously go out into industry, and so it's important that we're giving them skills. So just to finish, I think the equation up at the top is essentially the equation that we work towards. Our main focus within DiRAC is trying to deliver as much science as we can within the budget that we've got. And the way we do that is by co-designing the system so that they are designed around our science problems rather than just buying off the shelf. It also means we design our software around the systems that we're buying. And so it's the interaction of the two is key. What that means is we need more engagement between hardware in hardware and software co-design between our research community and industry. So what we always try to do in DiRAC is it's not a case that every academic has to work with industry, but anybody who wants to can, and that we try to make sure that all those industry partnerships are as productive as possible. So we're looking for problems which are actually of interest to both sides. And it's been very encouraging over the last few years to see how many academic colleagues who had no interest in talking to industry 5 years ago are now seeing actually we all have the same kinds of problems, and there are very interesting problems where the solution will benefit both an industry partner and the research community. The other thing we need to do is improve the training that's available and ensure that we're giving training to each other, so essentially benefiting from the training that's available in industry and offering training back based on our skills. So sorry for overrunning. But I think the thing I'd encourage everyone to do is, I mean, I'm happy to talk to people after this talk. I think on this front, it's very important we all work together in order to do that, in order to increase the amount of co-design that's going on so we get the best systems. And I'd look forward to seeing maybe all of you in Leicester in September. And I'll leave it there.